Hello everyone and welcome. Today I will introduce you to artificial intelligence, which is one of the tribe of artificial intelligence. In particular, I will show you how we can use evolutionary intelligence to discover failure in cyber-physical systems. As a case study, we will focus on self-driving cars, which is one of the very exciting examples of cyber-physical system with safety-critical requirements. A self-driving car is equipped with various sensors that aims to understand what's going on in its surrounding environment. Different sensors are in place to analyze different elements in the environment. Some of these examples include the distance with other cars, the traffic signs, the pedestrian, the lane, and so on. Sensors correspond to different features with machine learning components. In the case of camera sensors, machine learning is used to detect object and pedestrian from the video frames. Different features often use different specialized machine learning models. All these sensors continuously monitor the surrounding environment and send commands to the car controller, which is in the end in charge to make the final decision and to take an action, such as braking, accelerating, and so on. However, multiple features send contrasting commands at the same time, and therefore is crucial to design the controller in such a way that the safety critical requirements are always satisfied. What can go wrong if the controller is not extremely tested? Well, it can result in critical failures or accidents due to feature interactions. The consequences are unspeakable. We can have collision with other cars, accident that can be fatal for pedestrians, or not keeping the safety distance, not respecting traffic signs, lights, and etc. In this scenario, testing plays a very critical role. The most intuitive way to test self-driving cars is to drive one and monitor with a pair of hardware and software and see how it reacts when driving on the road. However, as you can imagine, this practice might be dangerous to the driver and can damage the very expensive hardware. For this reason, the very first testing happens via simulation. More precisely, the software is deployed and attached to a virtual environment that can simulate the road and all related physics. Testing via simulation is done with using a very sophisticated simulation engine, for example, Simulink in MATLAB, and designing specific test case scenario to simulate. The output of the simulation is a video where tester can observe the car, how it behaves while sitting safely on the couch. What is a test case in this context? Well, a test case is a specific driving scenario which may include the car to simulate, the shape of the road, the other car in the simulation, the position of traffic signs and lights, the position and speed of the pedestrians, the actual weather, and so on. All these elements are necessary since, for example, the braking time may change when different weather or temperature. As you can imagine, the space of all possible scenarios is extremely large, if not infinite. As such, tester cannot manually enumerate and try all possible scenarios. What we need is to find a feasible way to discover a few scenarios in which the car may fail as quickly as we can. Well, the solution is evolutionary intelligence, which evolve starting scenarios, often called seeds, toward failing scenarios of interest. Evolutionary algorithms use an iterative process with 5 main steps. First, initializing the search with seed scenarios. 2. Executing the initial test scenarios. 3. Selecting the most promising ones. 4. Creating variants of these scenarios. And 5. Just iterating through a loop feedback. To give a better idea on how evolutionary algorithm works, let's zoom in each step. The evolutionary process starts with a pool of test scenarios, and this scenario can be designed by a tester but also randomly generated. As explained before, each test scenario is a specific configuration of the environment in which the car will be simulated. Once the initial scenario or seeds are created, we can run the simulation and observe how the car behaves within the simulation. For example, each test scenario, we can monitor the minimum distance between the main car and the other cars in the simulation within the time window. Once we obtain the results of the simulation, we can select the scenario that is actually closer to violating one of the safety requirements. In our example, we have two test scenarios. In the first scenario, the minimum distance between the main car and the leading car is 2 meters, while in the second scenario, the minimum distance between the two cars is 1 meter. While both scenarios are safe, we can argue that the second test scenario is more interesting than the other one because it is closer to violating the minimum safe distance. Once we know how to select the scenarios, we can slightly change them to, for example, changing the weather, the shape of the road, the position of the pedestrian, and so on. The new test scenarios are then variants and can be used to initialize the next iteration of the evolutionary process. Here, the distance to violate the safety requirement is the main feedback for the learning algorithm. If you repeat the learning process a number of iterations, you will efficiently get into one of the failing scenarios. Does evolutionary intelligence really work? Let me show you an example of a failing test scenario we discovered in a real-world self-driving car system using exactly evolutionary intelligence. The scenario starts with a simulated car in very safe conditions. The main car is blue and is not visible yet at the beginning of the simulation, while the leading car is red. In this scenario, the blue car is in the middle of the crossroad with a speed limit of 80 km per hour. Initially, the speed of the blue car is within the speed limit, and the car also detects the red car and the pedestrian that is on the side of the street. Initially, the blue car is in warning mode as the pedestrian may cross the street in any moment. Therefore, the pedestrian protection feature takes full control. However, after a while, since the pedestrian is not moving, the car starts accelerating and the controller ignores the features for the safety distance. And this results in a collision between the two cars, the simulated one and the leading car. Well, today we have seen how to apply evolutionary intelligence to test self-driving cars. However, evolutionary intelligence is very handy and can be used for test traditional software, cyber physical system, mobile application, and much more. Just have fun!